Okay, so we've learned how to compute line integrals and how to compute integrals of vector fields. So let me just introduce Green's theorem. So let me first introduce a little bit more of terminology about parametrized curves. First, we already saw that a parametrized curve is called closed or a loop, like in here, if it begins and ends at the same point, like a circle or some more complicated path like this. A closed curve is simple if there are no intersections. Something that would be a loop but not simple would be if I start here and I go like this and then I cross and end up at the same place. That's not simple because it's self-crossing. Okay, so this is not simple. So the ones that are here are simple because they are not self-crossing themselves. Finally, they are positively oriented if it goes counterclockwise. So you see here that if I am here, then I start moving in the counterclockwise direction. It's a little weird when you are in this part to decide. But if you are in a very exterior point, then you can decide just locally, it looks like a clock that is moving counterclockwise. So if you are moving, so this is positively oriented, while this one, you can see that from here, we're moving in that direction, so it's moving clockwise, so it is negatively oriented. Okay? The orientation matters for the sign of integrals, as you have already seen, that if you do the integral from a to b of f of x, that is minus if you do the integral from b to a of f of x. So it's there's a matter of signs. And Green's theorem tells you that if you have a curve that is positively oriented, piecewise smooth, so either a smooth curve or just a bunch of sections of smooth curves, and you have a simple closed curve in the plane, and D be some region bounded by C, and P and Q have continuous derivatives. So let me first sketch. What are we talking about there? The curve C is positively oriented, so it goes like this in that direction. It's a loop. It's simple. It doesn't self-intersect. Then the interior is what we call D, is the region that is bounded by that curve C. And then you have two other functions, P and Q, with continuous partial derivatives in an open region that contains these. So there is some, larger area such that all of all these functions are at least continuous partial derivatives on something bigger than this region. Typically it's all of R2, but maybe there's some discontinuity out here, that's fine. Then it turns out that there is an equality of this line integral with a double integral. Now remember that this is a line integral, right? This is what we call the integral of f dr, is the integral of a vector field over C, with f being the vector field with coordinates p and q for functions. Okay? So it's telling you that there is a relationship between a line integrals, there's some vector field, you have a vector field in your border. It turns out that I can compute the value of that line integral by computing an area integral, a double integral of this other function that is relating the derivatives. Why is this important? Is because sometimes these line integrals are really nasty, but the double integral of area is really nice, or sometimes this integral in terms of area is really nasty, but the line integral is really nice. So this very interesting relationship between what's happening outside and what's happening inside it's a very useful mathematical tool. But in physics, it also has all sorts of consequences about, it turns out that some sort of like the sum of all the forces that are happening the outside gives you some measure of what's happening in the inside of the object too, in physical terms. So let me just try to. Well, I think I'm going to stop here for today, and we'll just do some of these examples next time.